I had technical difficulties during my talk. I want to thank the organizers for allowing me to present a recorded version. I also want to thank them for a wonderful meeting. I've enjoyed and learned a lot from listening to the talks here. I'm grateful for the invitation to speak. I want to tell you about neural network approximations of Calabi-Yau metrics. As this is a string phenomenology conference, the motivation for this talk is deeply rooted in our efforts to realize a real world from a string construction. The starting point is the MSSM, or some variant thereof. This is a modestly unreal world, has n equals 1 supersymmetry in 4 dimensions. A natural framework for accomplishing this is Calabi-Yau compactification down from 10 dimensions. And indeed, this has been one of the central paradigms for string model building since 1985. The topological features of the Calabi-Yau are sufficient already to take us rather far. For instance, the difference between the Hodge numbers H11 and H12 is computed by the index of the Dirac operator, and it tells us about the number of light generations in the spectrum. The Calabi-Yau I'll mainly be focusing on is the Fermat quintic. This is a manifold with H11 equals 1 Kähler parameter and H12 equals 101 complex structure parameters. This is an animation of the Fermat quintic embedded as a hypersurface before. We're looking at different sections of this manifold. Since 2005, there have been numerous semi-realistic constructions of the standard model. That is to say, they have the correct matter spectrum and the right interactions from knowing only the topology. It's useful to recapitulate what more we can learn by knowing the geometry as well as the topology. So the Kähler potential is not holomorphic. In order to determine the kinetic terms in low energy effective action and understand the normalizations of the fields, we need to have the metric. We also need the metric to deduce not just whether interaction terms are present, but how strong they are. So for example, to have a heavy top quark to determine the mass of the electron, we need to know the Yukawa couplings, and for that, we require the metric. As well, we're interested in the moduli dependence of the metric in order to address stabilization issues, but also to explore recent conjectures about the swampland landscape that we've heard quite a bit about at this meeting. The metrics we have right now are only numerical. There's no analytic metric on a Calabi-Yau threefold. These numerical metrics may or may not be good enough to calculate. We don't know. This program hasn't been pushed sufficiently far for us to tell. But we would like to get better numerical metrics in order to perhaps start doing some of these calculations. So we turn to machine learning as a new tool to develop metrics on Calabi-Yau manifolds. So machine learning has already had quite a few successes in high energy theoretical physics. So starting from 2017, big data has found a home in string theory. I'd like to briefly tell you about some other things I've looked at in this machine learning theme. Neural networks and support vector machines were able to determine the Hodge numbers of complete intersection Calabi-Yau threefolds. These manifolds are described by some configuration matrix that tells us the homogeneous polynomials in products of projected space. Initially, with 90% accuracy, we will determine H11 and chi for this data set of 7,890 complete intersection Calabi-Yaus. Later, Urban and Finatello were able to boost this accuracy to essentially 100%. Now, 7,890 is a large data set, but it's not a huge data set. There are 1.7 million hyperbolic knots up to 16 quasics. We're able to predict the volume of the knot complement starting from the Jones polynomial. We're able to do this with about 97% accuracy. This is about as good an accuracy as you can expect, because the Jones polynomial does not uniquely identify a knot. We've even reverse engineered what the neural network is doing to give us an analytic function that does almost as well. Because of the wealth of data and its relation to quantum field theory, knot theory has become a test bed for machine learning and high energy theory, and many groups are looking at different aspects of knot theory. Finally, closer to the real world, you can also approach QCD using machine learning. So Hashimoto and collaborators started this, and they were able to solve one problem, machine learn one problem, and use this to solve a different problem. And we'll revisit this when we discuss Calabi-Yaus. Their problem was using lattice data, the chiral condensate Bev against a quark mass. And from that machine learning task, they're able to develop the form of a quark anti-quark potential. In this spirit, with Gall, Mayorga-Peña, and Mishra, we looked at learning features in the baryon spectrum from training on the meson spectrum. This is consistent with Witten's idea that baryons are solitons in the meson spectrum at large n. However, this is n equals 3. There have been, of course, other works in machine learning and HepTH as well. So the protagonist here is the neural network. The idea behind a neural network dates back to Rosenblatt at the Cornell Aeronautical Laboratory and the Office of Naval Research. We essentially feed in an input vector into a perceptron or a neural network more generally, and we correlate this input vector to an answer. In training, we fix certain parameters of this neural network. These are elements of weight matrices and bias vectors. In the training, we extremize some loss function, and then we use the trained neural network to predict on unseen data. In passing from one layer of the neural network to the next, we have nonlinear activation functions, and this is what does the work of learning. All of this has been implemented in Mathematica after Mathematica 10, so there are out-of-the-box implementations that you can use to get started. We'll use slightly more sophisticated implementations in Python. But getting started here is very easy. In fact, a number of the projects I discussed earlier were done in concert with beginning students. In addition to the machines, my collaborators are Damien Mayorga-Peña and Challenger Mishra. Damien is a postdoc at WITS, and Challenger is at the University of Cambridge. They're both incredible people. I should also say that this effort to use numerical approaches to Calabi-Yau geometry has a extensive history. Starting with Hedrick and Wiseman and Donaldson, there have been efforts to find numerical metrics. And in addition, recently, machine learning has been brought to bear on this task. Ashmore, Hay, and Overett were able to use machine learning to improve the performance of Donaldson's algorithm. And about 3 weeks before our paper, 2 other papers appeared that also had machine learning successes in finding Calabi-Yau metrics. The paper by Anderson, Gerdes, Gray, Krippendorf, Raghuram, and Rula was discussed in this conference by Sven. That their work, in addition to looking at SU3 holonomy manifolds, was able to find metrics on SU3 structure manifolds. Recently, there have been some analytic developments in finding metrics on K3. So the geometries I'm going to look at are are realized by equations in projective space. The prototype is a torus, which is realized as a cubic in P2. K3 is a quartic in P3. We'll look at different quintics. The Fermat quintic and the Dwork quintic in particular. The Dwork quintic has a complex structure parameter psi in the defining equation. We'll in addition look at the Tian-Yau manifold. The Tian-Yau manifold is realized in terms of equations in P3 cross P3. This is interesting because firstly, H11 for this manifold is bigger than 1, and secondly, it has a history in string phenomenology. A freely acting Z3 quotient on this manifold gives a Calabi-Yau with chi equals -6, and some of the first string model building happened on this space. So I'll remind you the Calabi-Yau is a complex and Kähler manifold. The metric is obtained by taking derivatives of the the Kähler potential, and it can be used to construct the Kähler form. The Kähler form is closed. The Ricci tensor is given to us by taking derivatives of log det G. So Calabi conjectured and Yau proved the existence and the uniqueness of these Ricci flat metrics. So Calabi established that in a given Kähler class, there's a unique metric, which is Ricci flat, and Yau proved its existence. This proof, however, is not constructive. What Yau did was he solved some classical modular pair equation and showed that given the solution, you can attain a Kähler metric when C1 equals 0. Donaldson's algorithm is perhaps a numerical state of the art in computing metrics on Calabi-Yaus. The idea is to start from the Fubini study metric on projective space, which is Kähler and well understood. The pullback of the Fubini study metric onto the embedded hypersurface, however, is not Ricci flat. But it gives us a starting point for an iterative construction. So given an element of the basis of degree k holomorphic polynomials over M, we can construct a Kähler potential. We essentially realize a Kodaira embedding and use the Fubini study metric to proceed. The number of such basis polynomials scales like order k to the fourth for the quintic. So Donaldson's algorithm is for constructing what's a so-called balanced metric. This balanced metric is a fixed point of some iteration scheme. In the limit where k goes to infinity, the balanced metric that Donaldson provides approaches the Ricci flat metric. Numerical implementations of this have been established. However, they're computationally expensive. As well, we learn the metric at a point. We would like to understand issues of moduli dependence, so we'd like to go beyond this approach. We also want to establish how well we're doing, and there are different measures to let us do that. So we can write an expression of the volume in terms of the top holomorphic and anti-holomorphic forms on the Calabi-Yau. We can also write an expression for the volume in terms of the Kähler form. These expressions are proportional to each other. Knowing that, we can look at essentially the difference between these two ways of computing the volume. And the sigma measure will vanish when we achieve the Ricci flat metric. In addition, we want the Kähler form to be closed. The Kähler form is given to us by the metric, so we can essentially test whether this is closed. And this kappa measure should vanish for a closed Kähler form. Finally, as we're working on a manifold, we're using charts and atlases and so on. Going from one chart from one coordinate patch to another coordinate patch, we know that the metric transforms via the Jacobian. So M here measures a disagreement in the numerical metric on different coordinate patches. I'm labeling these patches by M and N. Zm is not equal to 0 is a condition on one of the coordinates in the ambient space. And since we have a hypersurface equation, Zn is a dependent coordinate in this equation. All right. So our strategy is to decompose the metric using the LDL decomposition. D is a diagonal matrix. L is a lower triangular matrix with ones along the diagonal. We'll give the neural network the metric of points in the manifold, and then we'll query the trained neural network at new points. This is slightly different from the traditional approach to machine learning in that we don't know the answer for the training set. Rather, we need to establish the answer for all points. So we'll initialize the metric at random, and we'll use as a loss function a linear combination of these different measures I described. So the sigma measure, which measures how flat we are, the kappa measure, which measures Kählericity, and the mu measure, which tells us whether the metric agrees on different coordinate patches. The implementation of the neural network uses two artificial neural networks. One is focused on D, and the other is focused on L. And we feed it the metric at different points on the manifold. the coding is done using PyTorch. All right, so one more thing, and then I can show you the results. So we need to choose points to study. So the approach for doing this is to use the structure of the projective space. So we'll start with we've started with a complete intersection Calabi-Yau in a single projective space, and we'll consider Pn and choose points where they we'll choose points, pairs of points, draw lines between those points, and see where they intersect the hypersurface. The lines are uniformly distributed with respect to the SUN+1 symmetry of the Fubini study metric. This approach has been used in various other investigations. All right, so choosing points in this manner, this is a selection of points on the torus. Using the neural network for the torus, we find the true flat metric and the predicted flat metric graphically look the same. They're essentially the same up to a rescaling. Here are 500,000 points on the quintic. What I've done is I've set the coordinate z1 equal to 1 and projected the other coordinates onto the z4 plane. Now, this is a rather dense collection of points. So here is the same data presented as a contour plot. We see that the coloration of this plot indicates that we're selecting points more strongly in certain regions than in other regions. If you compare this point selection of the Fermat quintic to the Dwork quintic with psi equals 10, we see that we're choosing points at different places. Here, I've set z1 equal to 0 and looked at the real parts of 3 of the other coordinates. And we notice that on the Fermat quintic, the curvature of the Fubini study metric is certainly non-vanishing. Okay, so results. This is the behavior of the sigma measure as a function of epoch. So in machine learning parlance, an epoch is one complete pass through the data set in training. So this plot shows the behavior of the sigma measure on training data and test data. The training data is in blue, the test data is in gold. The y-axis of the plot is logarithmic. The kappa measure, which again measures how close you are to having a closed Kähler form on training and test data, certainly shows a downward trend. So the approximation is getting better and better with the number of epochs. The mu measure, which looks at the overlaps, also decreases. All right, so combining all of these features into the loss function, this is the behavior on training and test data, and we see the test curve mirrors the training curve. The key feature in the behavior of this loss function is the sigma measure, which describes the flatness of our geometry. So in comparing a Donaldson, the flat metric we achieve corresponds to about k equals 16. All right, I mentioned that as we're learning the solution to one problem, we're often describing a second problem as well. So the Fermat quintic enjoys Z5 symmetries. So if we scale the coordinates by introducing a phase, which is a fifth root of unity, the metric shouldn't change. So we can test this. So as a consistency check, but also as an instantiation of learning while performing an auxiliary task, we look at what's happening on points that are related by this tau transformation, this Z5 transformation, and we look at points that are unrelated, and we see that the metrics at points related by this tau transformation agree. All right, so I want to say a few words about Tian-Yau. Now, I've only looked at a sigma measure, so I can't guarantee that the metric we obtained is in fact a good metric, but I've looked at the volume distribution of the training set before and after training, and the volume distribution of the test set before and after training. We see that the loss functions on training and test both decrease. Now, this is a manifold with H11 equals 14. So we don't have control of which Kähler class we land in when we use even the combined loss function that I talked about previously. We need to augment this loss function by extra conditions that preserve the Kähler class. And rather than initializing with random data, we should initialize with the Fubini study metric and try to preserve the Kähler class of the Fubini study metric as we learn the flat metric. We're working on this, and I hope to report a better metric on Tian-Yau and other manifolds at H11 bigger than 1. Now, one way to preserve the Kähler class in learning is to use Ricci flow. Ricci flow was famously used by Perelman to prove Poincaré's conjecture that every simply connected closed V manifold is homeomorphic to S3. Perelman solved this problem using Ricci flow with surgery. In Ricci flow with surgery, there's a parameter lambda, and if you take derivatives of the metric with respect to this parameter lambda, this is proportional to the Ricci curvature. So fixed points of this flow are Ricci flat metrics. In fact, Perelman considered gradient flow equations, which are obtained from extremizing some entropy functional. In order to write this entropy functional, he included an additional scalar degree of freedom, the dilaton. Verdin noticed long ago that Ricci flow is like renormalization group evolution of a nonlinear sigma model in the string world sheet with some target space metric. The modified flow equations are as written, and this flow preserves the Kähler class of the metric. So we can start in principle with a pullback of the Fubini study metric and solve the Ricci flow equations to get the flat metric. We can write a loss function that encodes these equations in motion. Take the loss function to be left-hand side minus right-hand side. The difficulty is that the modified flow equation we're looking at involves solving things in detail in a very complicated setting. The equation of the dilaton is a backward heat equation, whereas you're solving the other equation forward in time, if you like. We have preliminary results on this essentially by brute force, and we can show that we can get the flat metric on the torus. So what we're considering right now is how the metric changes as a function of complex structure parameters. We can do this for the Dwork quintic by varying psi, but we're interested in a more detailed look at this kind of thing. One thing to maybe look at is the mirror quintic. The mirror quintic has a single complex structure parameter. However, there are 101 Kähler parameters, so we need to determine how to preserve the Kähler class along the learning. As well, we can look at Tian-Yau and split bicubic and other manifolds with H11 bigger than 1. With Parabergler and Tristan Hupsch, we're looking at generalized complete intersection Calabi-Yaus of the type introduced by Anderson, Abruzzi, Gao, Gray, and Lee. With Altman, Gray, Hay, and Nelson, we took the Kreutzer-Skarka database of reflexive polytopes and triangulated these polytopes for manifolds at H11 less than or equal to 6. We have a database of Calabi-Yaus. We'd like to augment this database by including metrics on these spaces. Recently, McAllister and collaborators have come up with ways to triangulate Calabi-Yaus with H1 bigger than 7. And we can start looking at metrics there as well in principle. We like to study things like G2. Ultimately, we're after a realistic top-down perspective on the low energy effective action in string compactification. So that's a long-term goal of this program. The machine learning aspects are of interest broadly in high-energy theoretical physics. University of Witwatersrand will host String Data 2021 this December. So thank you for your attention.
Thanks for the very interesting talk. I had a couple of quick sort of technical questions. You mentioned you had two neural networks for two different parts functions within the metric, I gather.
Yeah.
Why didn't you just have it be fully connected and let it discover if it wants to do that or not? Have multiple outputs of a connected neural network, and if it wants to split its brain, it could determine that those weights should be 0. Is it somehow better to separate it by hand? Because I've seen that done before in differential equation solving.
I don't know about the general result of whether it's better to do it one way or the other. We did it this way because it happened to work for our case. We find that if we nudge the network along by teaching it the LDL decomposition, that might produce results. So we can import what we know in order to simplify life for the machines. But we can also let it discover things on its own as well.
Second question is, it seemed like sigma was getting stuck in a local minimum. Is that fair, or did you try different optimizers to get it to go down further, or?
We tried various things. It seems that after a number of epochs, it does seem to saturate. But the sigma component is a dominant feature in achieving a flat metric. So we'd like to do better there, of course, but we're trying various things.
Thanks.
Excellent. Any other questions for Vishnu? I just have a question regarding the Ricci flow. I haven't thought much about this, and well, there were some technical difficulties with your slides. So neural networks give us variational ansatzes for lots of things we care about, whether it be, again, these quantum states that condensed matter people do, or in your guys' case, metrics. The vast majority of the parameter space associated with this variational ansatz are not Ricci flat. And yet we have this Ricci flow equation that depends on only one parameter in the canonical context. Is there some sort of multi-dimensional generalization that one might be able to study in this context? Like you have some very large dimensional parameter space for the general variational ansatz, but there might be some flow on some greater than one dimensional subspace that's interesting.
That could well be the case. We've tried this for a while. We've been playing with Ricci flow for about a year now, but we haven't gotten very far in that we haven't really been able to get results on anything besides the torus. But we're trying. We think that this is a promising approach because it preserves the Kähler class. So you start with the Fubini study metric, you get the flat metric in the Kähler class again, in that Kähler class at the end of the flow.
Right. Right. Yes, you want to float another Ricci flat metric at the end of the flow. But okay, I see. Okay. Well, very good. I think I better think before I spontaneously ask questions further along this direction. It's interesting. I had heard that you guys were thinking about Ricci flow in this context, and was it already in your guys' first paper on the subject, or is it still in progress? I know that you only
had some comments in our paper, but we're still working on this, as I said, and hopefully we'll have some results to report in the next months, but we'll see.
Very cool. All right, well, thank you very much. Let's thank Vishnu one more time.